Representation Theory of Finite Groups, Lecture 8. Simple Characters. Let us start with a quick recap of what we did on the previous lecture. Let G be a finite group and V a G module. In the previous lecture, we defined the character of V as the function whose domain is G and the codomain is the set of all complex numbers, and the value of this function, denoted chi v, at the element G in G equals the trace of the linear operator which describes the action of the element G on the module V. So here are the basic properties of this function. The value of this function at the identity element is equal to the dimension of V. The function chi v is constant on all conjugacy classes of the group G. And if we have two isomorphic modules, then their characters are equal. We denoted by f from G to C the algebra of all functions from G to C. So this is an algebra with respect to the pointwise addition and multiplication. And we also denoted by Cf from G to C the subalgebra of this algebra consisting of all class functions. So, and now using the terminology of algebras, we have the following further properties of characters. The character of the direct sum of two modules V and W is equal to the sum of the characters of V and W. And the character of the tensor product of two modules V and W is equal to the product of the characters of the individual factors. So today we are going to create a new structure on this algebra of all functions from G to C and use this to derive very strong module theoretical properties. So recall that the overline denotes the complex conjugation. So what we want to do, we want to define a Hermitian inner product on our algebra of all functions. So for two functions alpha and beta, we define the angle bracket between alpha and beta as the following complex number. So we take 1 divided by the cardinality of G and then times the sum over all elements G in G, the value of alpha at G, times the complex conjugate of the value of beta at G. And the claim, this angle bracket defines a Hermitian inner product on our algebra FGC. Proof. It is clearly that the right-hand side of our formula is linear with respect to the first argument. Also, if we swap the role of alpha and beta, we should take the complex conjugate of the right-hand side, because we have a complex conjugate over beta, but not over alpha. So if we swap their roles, we should complex conjugate the right-hand side. So this checks the first two properties of inner products. It remains to check that our inner product is positive definite. So if we compute the angle bracket between alpha and alpha, so the outcome is 1 divided by the cardinality of G, sum over all elements G in G, alpha of G times the complex conjugate of alpha of G. So this product, alpha of G times its complex conjugate, is of course equal to the square of the absolute value of alpha of G. And this absolute value is a non-negative real numbers. So a sum of non-negative real numbers is a non-negative real number. So this shows that the angle bracket between alpha and alpha is a non-negative real number. And also this number is equal to 0 if and only if all summands are equal to 0, which means that the value of alpha at all elements G is 0. So alpha is the 0 element in our algebra. So this proves that our angle bracket defines a Hermitian inner product on our algebra of all functions from G to C. Now let us make a quick sneak preview to the main result of this and the next lecture. So our goal is to prove the following theorem. Let L1, L2, and so on Lk be a complete and irredundant list of simple G modules. Claim 1. The characters of these simple modules form an orthonormal basis in the algebra of all class functions. Claim 2. For any V in Gmod, the multiplicity of the simple module Li in V equals the inner product of the character of V and the character of Li. Claim 3. If you write V as a direct sum of simples Li with multiplicities Mi, then the inner product of the character of V with itself equals the sum of Mi squares over all I from 1 to k. Claim 4. A G module V is simple if and only if the inner product of the character of V with itself is equal to 1. And claim 5. For two G modules V and W, the fact that they are isomorphic is equivalent to the fact that their characters coincide. It is good to observe that this theorem rephrases a lot of algebraic properties and algebraic information like isomorphism or simplicity in terms of arithmetic information like one number is equal to another number or some number is equal to 1. So in particular, the last two properties are really extraordinary. It is usually quite difficult to check that some G module is simple. However, this theorem reformulates this property in terms that the scalar product of its character with itself is just 1. And similarly, in order to check that two modules are isomorphic, we just need to check that their characters coincide. So these are very strong properties where algebraic information is reduced to some numerical verification. And we will need a lot of preparation before we can prove this theorem. Let us start our preparation with the following observation. Let V be a G module and G an element in the group G. Then the value of the character of V at G inverse is equal to the complex conjugate of the value of the character of V at G. Proof. Recall that any element in the group acts on V diagonalizably, since G is annihilated by the polynomial x to the power the cardinality of G minus 1, and this polynomial does not have multiple roots. So therefore, we can choose an eigenbasis V for the action of G on V, which consists of elements V1, V2, and so on Vk, and let lambda 1, lambda 2, and so on lambda k be the corresponding eigenvalues. Then, the element G inverse is diagonalizable in the same basis, and the corresponding eigenvalues are simply the inverses for the eigenvalues of G. So these are lambda 1 inverse, lambda 2 inverse, and so on. However, since each lambda I has the absolute value 1, because it is a root of this polynomial x to the power the cardinality of G minus 1, it follows that the inverse of lambda I is equal to the complex conjugate of the lambda I. And this is true for each I. So now we can simply compute the characters. The character of V evaluated at G is just the sum of the eigenvalues lambda 1, lambda 2, and so on lambda k. And the character of V evaluated at G inverse is the sum of the eigenvalues for G inverse. So lambda 1 inverse plus lambda 2 inverse plus and so on plus lambda k inverse. So each lambda I inverse is just the complex conjugate of the lambda I. And the complex conjugate is an additive function. So we get the complex conjugate to the sum of all lambda i's, which is exactly the complex conjugate to the value of the character of V at G. Our next step is to define the notion of a dual module. So let V be a G module. Consider the dual vector space V star, or V dual, which is a space of all linear maps from V to the complex numbers. For an element alpha in V star, an element G in G, we define the element G alpha in V star via the following equality. So G alpha evaluated at V is by definition equal to the value of alpha at G inverse of V. Claim: this defines on V star the structure of a G module. Proof: it is very easy to check that the element G alpha defined in this way is actually an element in V star. So this follows from the linearity of the action of G inverse and the linearity of alpha. Now let us check that this action of G on V star is actually linear. So let's start by checking that it is additive. So if we apply G to the sum of alpha and beta and then evaluate it at V, so by this definition, this is equal to the value of alpha plus beta at the element G inverse of V. By the definition of the sum of two elements in V star, so this is equal to the sum of the value of alpha at G inverse of V plus the value of beta at G inverse of V. And using our definition, this is equal to the value of G alpha at V plus the value of G beta at V. And similarly, one shows that you can move complex scalars past this action of G. In other words, that the action of G is indeed linear. It remains to check the action axiom. So let us take two elements G and H in our group G and act on alpha by their product. So GH acting on alpha and then evaluated at V. By the definition of the action, this is equal to the value of alpha at GH inverse of V. But the inverse of product is the product of inverses in the opposite order. So this is equal to alpha evaluated at H inverse G inverse of V. So by the action axiom applied to the G module V, this is equal to the value of alpha at the element H inverse of G inverse of V. So now we have this H inverse here to the left, so we can rewrite it using our definition as H alpha evaluated at G inverse of V. And again, using our definition, this is G applied to H alpha and then evaluated at V. So GH of alpha is equal to G of H of alpha. So this verifies the action axiom and completes our proof. So please note, so here in our definition, the action of G on the dual module is essentially given by the action of G inverse on the original module. So if we choose a basis in V and the dual basis in the dual vector space V star, then the matrix of G with respect to this dual basis will be the transpose of the matrix of G inverse with respect to the original basis at V. So in particular, the character of the dual module is given by the character of the original module, but evaluated at the inverse element, which, as we already seen, is simply given by the complex conjugate of the character of the original module. And also we can remark the correspondence V sent to V dual defines an exact and contravariant endofunctor of G mod. So in fact, the notion of a dual module is a special case of the following more general construction. Let V and W be two G modules. Consider the space Hom CVW of all linear maps from V to W. For such a linear map alpha and G in G, define G alpha as a linear map from V to W, which is given by the following equality. So the evaluation of G alpha at the element V is equal to, so we should take G inverse of V, apply alpha to it, this gives us an element in W, and then we apply the element G, which acts on W because it's a G module. So this is the equality which defines G of alpha. Claim this defines on the set of all linear maps from V to W the structure of a G module. Again, because this formula is linear in G alpha and G inverse, it follows that G alpha is actually an element in Hom CVW. So let us check that this action of G on the set of all linear maps from V to W is linear. So we check first the additivity of this action. If we apply G to alpha plus beta and evaluate it to V, we get G of alpha plus beta applied to G inverse of V. So due to the fact how we add linear maps, this is equal to G applied to the sum of alpha of G inverse of V plus beta of G inverse of V. By the linearity of the action of G on W, this is equal to G of alpha of G inverse of V plus G of beta of G inverse of V. And using our definition of the action, this is equal to the evaluation of G alpha at V plus the evaluation of G beta at V. And similarly, one shows that this action of G is compatible with multiplication with complex scalars. So it is a linear action. Again, we have to check the action axiom. So what happens if we apply to alpha the product of G and H? So when we evaluate this at an element V, so by the definition of the action, this gives GH applied to alpha of GH inverse of V. Again, we use that the inverse of the product is a product of the inverses written in the opposite order. And now we can use the action axiom to write that H inverse G inverse evaluated at V is H inverse evaluated at G inverse of V. And similarly, GH evaluated at this long element alpha of something is G evaluated at H evaluated at this alpha of something. And now we can use the definition of our action. We have H evaluated of alpha, which is evaluated at H inverse. So this gives us H alpha evaluated at the argument of this H inverse, which is G inverse of V. And the same formula now applied to G gives us G evaluated at H of alpha and the whole thing evaluated at V. And this verifies the action axiom and completes the proof of our claim. And note that if W is the trivial G module C triv, then this gives us exactly the definition of the dual module V dual. So the general construction defines a bifunctor where you have two arguments which are G modules and you produce a G module, and one argument is contravariant and another argument is covariant. So now let us take an alternative look at the notion of a G-homomorphism. For a G module V, denoted by V upper G, the set of all elements V in V on which all elements in G act trivially. So G of V is equal to V. It is very easy to check that V upper G is a submodule of V. It's called the trivial part of V. It's a trivial summand. So V upper G is isomorphic to a direct sum of copies of the trivial G module. Claim: for all V and W in G mod, the space of all G homomorphisms from V to W is exactly the trivial part of the G module of all linear maps from V to W. Proof: so by definition, a linear map from V to W is a G homomorphism if and only if it commutes with the action of G. So for any G in G, applying G after alpha should be equal to applying G before alpha. So if you take this equality and multiply it with G inverse on the left, we can rewrite it as alpha is equal to G inverse after alpha after G for any G in G. And by the definition of the action of G on the space of all linear maps from V to W, this means exactly that alpha belongs to the trivial part of this G module. Okay, and now we describe how we can take a G module and find this trivial part. So let G be a G module. Then we have the linear map theta from V to V, given by the following formula: 1 divided by the cardinality of G, and then the sum over all G in G, and then we take the linear operator, which is given by the action of this little g on our module V. Claim: the map theta is a projection from V to its trivial part V upper G, in the sense that the image of theta is equal to V upper G, and the restriction of theta to V upper G equals the identity map. Proof. So we have already seen that if we take an element H in the group and multiply with this symmetrizer 1 divided by the cardinality of G and then the sum of all elements G in G, we will get this symmetrizer back, because we will get here the sum of all H times G, but multiplication with H is just a permutation of elements in G. In particular, it implies that if we apply the element H to anything which is in the image of theta, then nothing happens. In other words, that the image of theta is inside V upper G. At the same time, if we start from an element from the trivial part V upper G, and if we apply theta to it, then we get the formula 1 divided by the cardinality of G, the sum over all elements G in G, and then we take G of V. But V is in the trivial part, so G of V is equal to V. So we have the sum of V taken the cardinality of G times, and then we divide by the cardinality of G. So we get our V back. So, and this implies that the restriction of theta to the trivial part of V is the identity map. The next step in our preparation is a comparison between the tensor product of two modules and the home module. Proposition: for two modules V and W in G-mod, we have an isomorphism of G modules. So the G module of all linear maps from V to W, defined a couple of slides ago, is isomorphic to the tensor product of the dual module for V and W. Proof. Let us first note that both spaces have dimension dim V times dim W. So this is pretty obvious. So consider the linear map phi from the tensor product to this home CVW module, which sends the element alpha tensor W to the linear map phi with the index alpha tensor W, which is defined as follows. So when we evaluate phi alpha tensor W at V, we get alpha of V times W. Note that the formula alpha of V times W is obviously linear in alpha, in V, and in W. So this means in particular that phi with the index alpha tensor W is indeed a linear map from V to W, because this formula is linear in V. And this is true for any alpha in V star and for any W in W. And it also means that defining phi on all elements alpha tensor W gives rise to a unique linear map from the tensor product to home CVW. And this is because the tensor product is by definition linear in alpha and it is linear in W. So this means that phi is a well-defined map. So this is a well-defined linear map from V star tensor W to home VW. So next, let us prove that phi is surjective. Fix a basis V, V1, V2, and so on Vk in V, and a basis W, W1, W2, and so on Wm in W. Denote by psi ij the unique linear map from V to W which is defined as follows. So the value of psi ij at the basis element Vs is equal to the Kronecker delta of j and s times wi. So for each I from 1 to m and for each j from 1 to k, we have such unique linear map. So in fact, since we have chosen the basis of V and the basis in W, then the set of all linear maps from V to W is isomorphic as a vector space to the vector space of all m times k complex matrices. And then our linear maps psi ij correspond exactly to the matrix units. So they correspond to a basis in this space of all linear maps from V to W. Also note that this psi ij is equal to phi of alpha tensor Vi, where alpha is an element in V star such that it sends Vs to delta Js for all s, and Wi is our element in the basis W. So in particular, the image of phi contains a basis of the space of all linear maps from V to W. And since phi is a linear map, it means that phi is surjective. But since we already know that the dimension of the space of all linear maps is equal to the dimension of the tensor product of V star and W, it follows that phi must be bijective. Any surjective linear map between two vector spaces of the same dimension is necessarily bijective. Finally, let us check that phi is a homomorphism of G modules. So let G be an element in the group, alpha an element in V star, and W an element in W. Then G applied to the tensor product of alpha and W by definition is equal to the tensor product of G alpha and G of W. So the corresponding phi, the phi which corresponds to G alpha tensor GW, evaluated at V, again by definition, this is G alpha evaluated at V times G of W. So this is just for the formula defining phi. And using the definition how G acts on alpha, so G acting on alpha and then evaluated at V is equal to alpha applied to G inverse of V. So this is an element in W which we get by evaluating phi corresponding to G alpha tensor G of W at V. On the other hand, let us evaluate at V the linear map G of phi of alpha tensor W. To compute this, we should evaluate G at the evaluation of phi of alpha tensor W at G inverse of V. And this is equal to alpha of G inverse of V times W. But since alpha of G inverse of V is just a scalar, we can move it out and get alpha of G inverse of V times G of W. And this is the same thing as the right-hand side of the previous equality. Consequently, G applied to phi associated to alpha tensor W is equal to phi associated to G of alpha tensor W. And this means exactly that phi is a homomorphism of G modules. So let us now recall our main theorem. So what we want to prove? We want to prove the following. So assume that we have a complete and irredundant list of simple G modules. Then the characters of these simple modules form an orthonormal basis in the space of the class functions. The multiplicity of a simple module in any module V is given by the inner product of the character of V and the character of the simple module. So if we write V as a direct sum of simple modules with the corresponding multiplicities, then the scalar product of the character of V with itself is just the sum of the squares of the multiplicities. A G module V is simple if and only if the character of this module has length 1. And two G modules are isomorphic if and only if their characters are the same. Okay, so this is what we want to prove, and a major part of the theorem will be proved in this lecture. So let us start with proving a part of the first claim. Claim: if V is a simple module, then the scalar product of the character of V with itself is equal to 1. Proof: by Schur's lemma, 1 is equal to the dimension of the space of G-homomorphisms from V to V. We know that the space of G-homomorphisms from V to V is exactly the trivial part of the G module of all linear maps from V to V. And we also know that the map theta, so this is 1 divided by the cardinality of G, the sum of all elements G in G, it projects the whole module of all linear maps from V to V to the trivial part of this module. So the dimension of the space of all homomorphisms from V to V should be equal to the trace of this linear map theta for the module hom C VV. So by the definition of the map theta, its trace is equal to, so 1 divided by the cardinality of G, this is linear, we can move it out, and then we have the sum over all G in G, trace of the element G acting on this module hom CVV. But we also know that the module hom CVV is isomorphic to the module V star tensor CV. So we get 1 divided by the cardinality of G, sum over all elements G in G, trace of the linear map G on the module V star tensor V. Using the basic properties of characters, the trace of the action of G on the tensor product of two modules is just the product of traces on each individual component, and the trace of G on the dual module is just a complex conjugate of the trace of G on the module V. But then the formula which we obtain, this is exactly the scalar product of chi V with itself. So the original 1, which we started with, is indeed equal to the scalar product of chi V with itself. And this proves our claim. Let's go to the other part of the first claim. So if V and W are two non-isomorphic simple modules, then the scalar product of their characters is 0. So by Schur's lemma, 0 is equal to the dimension of the space of G-homomorphism from V to W. And now exactly the same argument as in the previous slide gives that this dimension of the space of G-homomorphism from V to W is equal to the complex conjugate to the scalar product of the characters of V and W. So this is equal to 0, so the scalar product is a complex conjugate of 0, which is 0. So this proves that the characters of simple G modules form an orthonormal system in the space of class functions. So this is a part of the first claim. This is enough to prove the second claim. So now for any G module V, the multiplicity of Li in V equals the scalar product of the character of V and the character of Li. Proof: let us write V as a direct sum of Lj's with multiplicities Mj's. Then the character of V is equal to the sum over all j from 1 to k, Mj times the character of Lj. Now, if we take the scalar product of this equality with the character of Li, and use what we already know, that the characters of Lj's are pairwise orthogonal, so all summands will disappear, and the only thing which will be left is Mi times the scalar product of the character of Li with itself. And we already know that this is 1. So this proves this claim. Third claim: if we write V as a direct sum of Li's with multiplicities Mi's, then the scalar product of the character of V with itself is equal to the sum of the squares of the multiplicities. Proof: it's just a direct computation. The scalar product of the character of V with itself is the scalar product of the sum over I from 1 to k, mi, the character of Li, with itself. So due to bilinearity, we can write it as a sum over all I and j, mi times mj, and then the scalar product of the character of Li and the character of Lj. But this is the Kronecker delta, so the different things disappear, and the same things will give us 1. And the outcome is just the sum over I from 1 to k, mi squared. Fourth claim. A module V is simple if and only if its character has length 1. So the only if part is already proved in the first claim. So let us prove the if part. So assume that the length of the character of V is 1. So let us use the Maschke theorem. We write V as a direct sum of simple modules with some multiplicities. And then from the previous claim, we get that the sum of the squares of the multiplicities is equal to 1. But each multiplicity is a non-negative integer, so the only way to write 1 as a sum of squares of non-negative integers is when one of them is equal to 1 and the rest are 0. But then it means that V is isomorphic to the corresponding simple module Li. So this should be the same I as here. And finally, the fifth claim. Two G modules are isomorphic if and only if their characters are equal. And the only if part is one of the basic properties. So if two modules are isomorphic, then the characters are equal. So there are no problems with that. So let us prove the if part. So let us assume that we have two modules V and W whose characters are equal. But then if we take the scalar product of this common character with any simple module, we will get the same number, of course, mi, which means that the multiplicity of each simple module in V and W is the same. So in particular, both V and W is isomorphic to the direct sum of these simples Li with this common multiplicity mi. And this proves the claim. So from the big theorem, the only thing which is not proved is that the characters of simple modules span the algebra of class functions as a linear space. So this will be proved in the next lecture. Let us look at a quick example. Recall the extended character table of S3. So here I write the value of each character at all elements, because when we take the scalar product, it's very useful to have the value at each single element rather than the conjugacy class. Let us take the usual scalar product for rows in this table. So if you take the different rows, so here we have 1, minus 1, minus 1, minus 1, plus 1, plus 1. So the scalar product between the first and the second row is 0, the usual scalar product. And the usual scalar product between the second and the third row, 2, 0, 0, 0, minus 1, minus 1, it's also 0. So in fact, if you take two different rows, it's very easy to check that the usual inner product is 0. So now if you take the row with itself, you will have 1, 1, 1, 1, 1, 1. The sum is 6. And here we have 1 minus 1 squared is 1, 1, 1, 1, 1. The sum is 6. Here we have 2 squared, 4, 0, 0, 0, 1, 1. The sum is again 6. So the inner product of each row with itself, the usual inner product, gives us 6, which is exactly the cardinality of S3. And we recall that in the scalar product which we defined, we had this factor 1 divided by the cardinality of G. So it follows that all rows in this table indeed have length 1 with respect to the correct inner product when we take into account this factor. And let us also remark that the complex conjugation doesn't play any role in this example simply because all entries in the character table are real numbers. So the complex conjugate does nothing to them. Okay, let us finish with some problems and questions. Question 1. Fill in all the details in the proof of the G-module structure on the space of all linear maps from V to W. Question 2. Prove with all details that the trivial part of V is a submodule of V. Question 3. Compute the character table of Z3 and check that the rows are orthonormal. Question 4. Check that the rows of the character table of D2 times 4, which was computed in the previous lecture, are orthonormal. And question 5. We know that the character of the natural Sn module is given by the number of the fixed points of a permutation. Compute the inner product of the character of the natural S3 module n with the character of all simple S3 modules and compare the outcome to the known decomposition of n into a direct sum of simple modules. Thank you very much and see you next time.